Right, welcome to VLSI Design. This is lecture 8-4, the fourth lecture from chapter 8. Right, we are discussing effect of scaling. In our previous three lectures, we studied NOT with scaling factor 1, NAND 2 with scaling factor 1, and NAND 2 with scaling factor 3. We discussed rise and fall time delays for all these three circuits individually. Today, we'll study rise and fall time delays of a NOR 2 gate with scaling factor is equal to 1. We know that for the standard NOT with M is equal to 1, the basic gate TR is represented as TR0 plus alpha P times CF and TF as TF0 plus alpha N CL. So TR0 and alpha P are equal to these two expressions for a standard NOT with M is equal to 1. Since we are going to derive rise and fall time delay expressions for this circuit, where we have these two transistors in series, each of the two has a resistance Rp, whereas the two NMOS transistors are connected in parallel with individual resistance Rn. So to convert this expression into the TR0 for NOR2, I'm writing M is equal to 1 here. So for M is equal to 1 NOR2, this 2.2 is unchanged. What's about Rp? This Rp turns into 2Rp because in order to turn this chain on, both Rps have to be on. So this would be represented as 2 times Rp. First about CFET. Here we have this transistor, this and this, three transistors connected to the output. Each of these contributing its drain capacitance. Whereas we have discussed in the earlier lecture 8.3 or 8.2 that for a standard NOT there are only two transistors connected to the output. This means there are only two drain capacitances. So in that case we have 2, here we have 3, so the factor becomes explained in earlier lectures. The equivalent factor becomes 3 by 2. So this is 3 by 2 times CFET. This 2 cancels with this 2. So we are left with this factor 3. So this whole 2.2 Rp CFET is TR0. So this is 3 times TR0. Right. What's about alpha P for NOT2? How is it different from the standard M is equal to 1 NOT? Here we have already discussed, here we have 2 Rp instead of Rp because in the worst case, we have to have these two transistors on and these two Rps have to be in the path, increasing its resistance to 2 resistance of the path to 2 Rp. This means it is 2 times alpha P. So now we can write the expression for rise time delay of NOR2 with M is equal to 1. TR of NOR2 is its TR0 NOR2, which is 3 times TR0 plus It's alpha p, which is 2 times the standard alpha p times CL. So we have done half of the required work, completed the expression for the rise time delay of this node 2. Let's write the expression for the fall time delay. The fall time delay of a node with m is equal to 1 is, we all have already studied, is 2.2 Rn CFET. Now we are going to convert it into TF0 for node 2 with m is equal to 1. In this case, we have two resistances in parallel, Rn in parallel with Rn. In worst case, only one of them is on, so Rn remains Rn. And CFET, we have already discussed, becomes 3 by 2 times CFET. So this is 3 by 2 times CFET. So this whole stuff is TF0. So TF0 for node 2 is 3 by 2 times CF0 for standard node. This is 3 by 2 times TF0. What is alpha n? Alpha n for standard node is 2.2 times Rn. Alpha n for node 2, the worst case, in worst case, only one of them is on, only one of them comes in the path, the expression remains the same luckily. It becomes alpha n. So alpha n for node 2 in worst case is the same as alpha n as it is for standard node with n is equal to 1. So now we are ready to write the fall time delay for this node 2, which is 3 by 2 times the TF0 value we obtained for standard node plus alpha n, the same alpha n as we have for the standard node times CL. Right, in this lecture, this is all for this lecture by the way, and in the coming lecture, we'll study node 2 for m is equal to 3 and for m is equal to for any general value of k. Thank you.